Before continuing with the lesson, please take out this handout so you can follow along. In the last two lessons, we looked at experimental probability and theoretical probability separately. Now we're going to be looking at different techniques that we can use when dealing with any kind of probability type question. So to begin with, I'd like you to figure out the theoretical probabilities for all of these given events. So first off, you're going to be rolling a single die. Next, you're going to be rolling 2 dice. And just to help you out with 2 dice, I've given you the chart that I gave you before, where you have all the possible outcomes for rolling 2 dice. So write your probabilities as a fraction and as a decimal for each. Pause the video and do it, and then see how you do. So hopefully you were able to come up with this. If you're rolling a single die, well, how many possible ways can you roll a 1? Well, there's only one way. How many ways can you roll a 2? Only one way. How many ways can you roll a 3? Only one way. They're all the same probability. Each outcome, each event is equally likely. That's how we would read that. So when you're rolling a single die, there's no advantage to betting one number over another because they're all equally as likely. When you're rolling 2 dice, though, you can see each event has a different probability. The most likely event is rolling a 7. Although that's still only about 16.7% probability, it is the highest probability for any single number as a result. So if you got a different answer for any of these, you should pause the video and let me know so that I can come over and help you figure out what went wrong before you move on. Otherwise, take a look at the bottom of the page. It says use the online simulator at this address to calculate the experimental probabilities of the same events. Compare those results to the theoretical probabilities calculated above. And what do you notice? So you can go ahead and do that. Run a few different trials for rolling a single die. Run a few trials for rolling 2 dice. And see if your probabilities match up with the theoretical probabilities that you just figured out. So if you do that, hopefully you'll notice that as you do more trials, the experimental probability gets closer to the theoretical probability. The takeaway message here is that experimental probability, so probability calculated based on an experiment or trials of a simulation, that probability can change depending on how many trials you do. So the more trials you do, the more accurate your experimental probability will become. It approaches what the theoretical probability is. Now, in previous lessons, we've looked at how to figure out theoretical probability by using different charts and counting up how many outcomes there are, things like that. But I want to show you 2 more techniques for some more complex probability type questions. And those 2 techniques are what we call tree diagrams and the idea of the complement of an event. So I'll show you a tree diagram in the next example, but just briefly, the complement of an event is, well, if it's not one thing, then it has to be the other. So for example, let's say the probability that it's going to rain today is 40%. So what's the probability that it's not going to rain? Well, you intuitively know that's 60% because all the probabilities of all the events that are possible have to add up to 100%. So that's the idea behind the complement. If you want to find the probability of a certain event, you just eliminate the probabilities of everything else that could happen. Okay, so let's take a look at the examples below. The first one. What is the probability that when you flip a coin, 3 times, heads will come up twice. So this is kind of a complicated situation to think about just in your mind. So when you have a situation where you're flipping a coin 3 times in a row, each time you flip the coin, there's 2 possible outcomes, but each time you flip the coin, you're kind of compounding the difficulty of figuring out what the probabilities are. So this is where a tree diagram becomes helpful. So I'm just going to show you the tree diagram, and then I'll talk about it. So here it is. We're flipping the coin 3 times. So on the first flip of the coin, there's 2 possible outcomes. I could flip heads or tails. So let's say I flipped heads the first time. When I flip the coin this next time, I could either flip heads or tails. Let's say that I flipped heads first, then I flipped heads again. Well, the third flip could either be heads or tails. Now, if the first flip was a heads and the second flip was a tails, the third flip could either be heads or tails. The first flip could be tails, then the second flip could be heads, and the third flip could be heads, or I could go tails, heads, tails, or I could go tails, tails, heads, or I could go tails, tails, tails. These are all the possible ways you can flip 3 coins. So you can see each different pathway is a different outcome. So the question is, what is the probability that when you flip a coin 3 times, heads will come up twice? So we have to look at all the different pathways and find which ones have heads twice. Well, heads, 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 that's not 2 heads, that's 3. Heads, heads, tails, that pathway gives you 2 heads. Heads, tails, heads, well, that one works too. Heads, tails, tails, that's not 2 heads. Tails, heads, heads, that works. Tails, heads, tails does not. Tails, tails, heads does not work. Tails, 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 there's no heads at all. So if we want to find the probability of 2 heads, we need to find out how many possible successes are there. Well, there's 3 possible outcomes that give us success. And then on the bottom of the fraction, we have the total number of possible outcomes. Well, how many different ways can you flip 3 coins? There's 8 different pathways you can follow on the tree diagram. That's 8 different possible outcomes for 3 flips of the coin. So our probability is 3 out of 8. The next question says, what is the probability that when you flip a coin 3 times, heads will come up at least once? Notice it's not asking the probability when heads will come up once. It's at least once. So what does that mean, at least once? Well, it means once or twice or 3 times. So to find the probability of this, you could count up the number of outcomes where you get 1 head. You could count up the number of outcomes where you get 2 heads. You could count up the number of outcomes where you get 3 heads, and then add all those together to get the total number of ways you could get heads at least once. Or you can use the complement. What is the complement of getting at least 1 head? Well, the complement would be everything that's not that, which would be no heads at all. So we can find out the probability of no heads. That only happens once, tails, tails, tails. So there's a 1 out of 8 probability of no heads, which means the probability of at least 1 head would be 7 out of 8. Everything else that's not the complement. So some people find this idea of the complement a little bit confusing, but if you can wrap your head around it, it actually can make your job a little bit easier in certain instances. So here the idea was, if no heads is 1 part out of 8, the remaining 7 parts would be the complement of that. So the probability was 7 out of 8 that it was at least one head. The last two examples, we're going to switch gears. We're going to go back to dice. We're rolling 2 dice. So that chart that you have with you on the front of the page of all the possible outcomes when you roll 2 dice, that might come in handy for this. What is the probability that when you roll 2 dice, you do not get a sum of 2 or 11? Well, you can look at the chart, you can count up all the instances that are not 2 and not 11. That's a lot of counting because there's a lot of possible outcomes. Or you can use this idea of the complement. How many ways can you roll a 2? Well, that only happens one way. How many ways can you roll an 11? Well, that happens 2 ways. So the probability of getting a 2 or 11 is 3 out of 36. So what's the probability of getting not that? So everything else. Well, if 3 out of 36 is this, 33 out of 36 has to be everything else. And of course, once we have our fraction, we have to make sure it's in lowest terms. So this is actually 11 over 12. So we would say the probability of not rolling a sum of 2 or 11 is 11 out of 12. I'd like you to try this last question on your own. What is the probability that when you roll 2 dice, you get a sum between 4 and 10? And I just want to clarify, when I say between 4 and 10, I mean you can roll a 4, a 5, a 6, a 7, an 8, a 9, or a 10. So pause the video, try to find the probability, and then you can check back and see how you did. So I'm showing you 2 different ways you can answer this problem. You can just do straightforward, the probability of getting a 4 all the way to 10, you just add up. There's 3 ways you can get a 4, 4 ways you can get a 5, 5 ways you can get a 6, 6 ways you can roll a 7, 5 ways you can roll an 8, 4 ways you can roll a 9, and 3 ways you can roll a 10. That adds up to 30 different outcomes that give you success out of the 36 possible outcomes, and that fraction reduces to 5 over 6. So that's the probability of rolling between a 4 and a 10. The other way you can attack this problem is to use the idea of the complement. This is a lot of different outcomes to keep track of. What is not this? Well, it's rolling a 2, a 3, an 11, or a 12. Well, there's 1 way you can roll a 2. There's 2 ways you can roll a 3. 2 ways you can roll an 11. 12 ways you can roll a 1. So there's 6 ways you can roll not between 4 and 10 out of the 36. And that's the complement. So to find the probability of what we want, we would just take that away from the whole, which leaves us with 30 out of 36, which we had before, which reduces to 5/6. Now, you don't have to write out all of this. I'm just trying to show my thought process here. The probability of getting between 4 and 10 is the total number of outcomes minus the complement. And you can kind of do that part in your head. As long as you end up with 30 out of 36, you're good to go. So the whole point of this lesson was to introduce you to new techniques for dealing with certain probability problems. You might have to create a tree diagram when you're faced with different choices that are possible, or like we did where you're flipping a coin a certain number of times in a row. You can map out all the possible outcomes using a tree diagram. And sometimes when you're asked for a probability that is quite large for counting up certain numbers, you can use the complement to simplify your task. If you have any questions about this, let me know and I'll do my best to help. Otherwise, move on to the practice questions.